Hey everybody, this is Mr. Moideen. Hope everyone's doing all right. We're going to be moving into three-dimensional shapes in this unit, so a revisit of things you learned in earlier grades, maybe even before school started in preschool, prisms and spheres and cylinders and things like this in the context of area, which of course we just recently talked about. So, surface area. Before we get to the nuts and bolts, let's do a brief review and make sure we're on the same page when it comes to kinds of solids. The most familiar kind of prism that most of you are familiar with is probably the rectangular prism, your classic box. However, prisms can be really any shape, typically a polygon, that is translated. So for example, if I drew, let's say, sort of a random shape here, oops, and then translated it, I could then find, or I could then define a prism as being that sort of stretched out oblong object. That would be a strange prism, but it would be a prism nonetheless. For example, maybe a more illustrative one, if I had a triangle, let's say, and then I translated it over here, and then connected the vertices, that is also a prism. So a rectangular prism, the classic box shape, is the most familiar kind, but the blue shape is also a prism, and so was the green shape. A cylinder actually is in the prism family. Most people don't learn of it this way, but and it's useful to think of it as something separate as well. But a cylinder really is just a circle prism in the sense that you take a circle, you translate it almost like a slinky and just stretch it back, and now you have a cylinder. So it's a circle prism if you think of it that way, right? The bases are the same shape. Notice that in, going back to the prism for a second, the top base and the bottom base are the same shape. And the same is true in the cylinder as well. The shape just happens to be a circle. A sphere is what you get when you revolve a circle around its own axis. So a sphere would look something like this. And we typically put a dotted line around the hemisphere, or equator here rather, to indicate a little bit of depth. From circles, you also get cones. So imagine we have a circular base here, sort of looked at in relief. So that's why it looks sort of in perspective, not a perfect circle. Now I can think of a cone as sort of like picking up a cylinder, or sorry, a circle from the center and kind of pinching it upwards to make that happen. So imagine picking up the center here and just pinching it upwards, sort of like lifting up a tent, once you've laid it out. So a cone looks something like this. Pyramid is related to a cone in the sense that you could have some kind of polygon base. Let's say I had a hexagon base. And likewise, take the center and just pinch it upwards, and you would have a hexagon pyramid. Not drawn very well here. I'm a lot better with pencil than I am with this cheap stylus. More familiar pyramids, of course, have 4 sides at the bottom, the base. But in any case, any polygon will do for making a pyramid. So just some basic terminology here. I want to make sure we're on the same page. One thing that I want to make sure we also understand before we get to the formulas is lateral area versus the overall surface area. So here we have a variety of prisms, just to keep things simple for now. The lateral area would be just the sides. So if you know football, you know lateral means to the side, and in general, lateral means side anyway. Like a fish has a lateral line along its side. So, excuse me, lateral means side. Miswrote here. The lateral area would be the sum of all of these sides here. So if I just added these guys together, that would be the lateral area. However, the total surface area refers to the entire, as you might imagine, total. So surface area refers to all the stuff added together. So if you had to kind of define it, the surface area would be the lateral area plus the bases, the congruent shapes that have been translated. the top and the bottom in these diagrams. Now, prism surface area is probably something you saw in earlier math classes, maybe even elementary school. It's really, really simple. When it's not a rectangle, you may have to use a formula, but even then you can do it without a formula. But something like this, and we'll do more proper examples during Zoom class, but really you just think of this as the 6 sides of this box. So you have 2 sides that are, there's a bit of color here, 9 by 6, right? So 2 sides are 9 by 6 in terms of their dimensions. 2 sides are 6 by 4, the left and right of this box in dimensions, and 2 sides are 9 by 4, the top and the bottom. So you have 6 sides in total. You just get the areas of each of those 6 rectangles. So imagine deconstructing this into what we call a net, and you would have something like this, right? You can draw it more accurately. And of course the top itself, which I've left off here. So this would be the bottom, the left, the right, the front, the back, and then the top. So you find the areas of each one just using the basic rectangle formula from, basic math, and you can find the total surface area. And many problems are best approached that way, just by thinking about it reasonably and finding the surface area that way. A shape like this, likewise, you could find the area of this triangle. So the area of this triangle is 1/2 base times height, and there's 2 of them. So you find the areas of each one, the front triangle and the back triangle. But of course, there's also these 3 rectangles. So the lateral area, using that new term, would be the sum of these 3 rectangles, which again, you can reason your way through and figure out what the areas of each one of those are. They're not necessarily all the same, so you gotta be careful, but you have 3 rectangles and you have 2 triangles. Just find the areas of each and add them together, and that would be the surface area. That being said, there is a formula for this which may help you a little bit. Let me erase some of these numbers because we don't really need them. Just using this diagram. If we call this the height, which might be a bit of a misnomer because it's laying on its side, but imagine this tent shape was turned upwards. So let's call it the height, just sort of generically. Then what you can do is find the surface area this way. The surface area would be the perimeter of the base. So we're defining this length here as the perimeter. Let's make this black. So again, this is the perimeter of the base times the height, and that right there will give you the lateral area. So this is all of those rectangles on the side added together. So this is the lateral area. But then we also have the 2 bases to think about. So if you just think about the base area as this blue space here and this blue space here, that would be +2 times the base area. In my opinion, and this is totally my opinion, I think this formula is a kind of overkill. It's more formulas than you kind of need to know, but it may help. So I want to make sure you're familiar with it. I think in general, if you're able to deconstruct a shape in your head, or even with some manipulatives, it's easier to think about surface area just as the sum of all of these surfaces. But this does it too. A cylinder has a surface area that is a little more complex. The formula is right here. The surface area of a cylinder is 2 pi r squared plus 2 pi r h. I want to take a minute and show you why this formula is correct. So if you take a look at the video here with this animation, you'll see the deconstruction of a cylinder into its 3 constituent parts. The 2 pi r squared is the 2 circles, kind of a no-brainer, and the rectangle label of the soup can, so to speak, is 2 pi r times h. Now look carefully as it plays again where that 2 pi r comes from. The height is the height. The 2 pi r is the circumference of the circle. We've seen that formula before. The circumference of a circle is 2 pi r, and that's the width of the label. It has to go all the way around when you unravel it. So 2 pi r would be this length right here. The height is the height, both of the cylinder and of the label when it's deconstructed. So the area of this entire rectangle, length times width, is 2 pi r h. You also have two circles to deal with, so their areas, pi r squared, and there's two of them, and that's exactly where this formula comes from. Again, the key thing to recognize in terms of the y here is this part is the circumference. That's this length right here that the label goes all the way around on this metaphorical soup can. You can also see here where the perimeter times height plus 2 base formula from a moment ago kind of comes into play. The perimeter of a cylinder's base is a circumference, and we're multiplying it by the height, and we have two bases, so kind of the same thing. Cones have this other length, which we call a slant height. So this guy here called L in the diagram, this is called a slant height. I don't know why we don't usually call it S. I guess S is easily mistaken for 5. So we call this L, usually, the slant height, which you can see is longer than the actual height. And you might also notice that the way to find the slant height, if you're not given it, is to use Pythagorean theorem, because you have a right triangle formed between or among the radius, the height, and the slant height. So the formula for the surface area of a cone is a little involved in the sense that the area of the base is pretty straightforward. It's a circle, so this is pi r squared. The shape in blue here we've seen before. It's part of a circle, which we call a sector. And the area of this sector, even though we used proportions in the past accurately to find the area, there's another way to find this. And the way to do that is to use the formula pi r L. Pi times radius times lateral or slant height. So again, L is labeled in the same place here. So this would again be the lateral area of the cone. It's the slanty part, so to speak. So the total surface area, remember surface area is the lateral plus the base, would be pi RL plus pi r squared, where this part of the formula comes from the circle, and this part of the formula comes from the lateral part, the slanted part of the cone. So there's the critical formula there. Earlier we had this critical formula. Let's take a look at the pyramid next. The pyramid formula is a little interesting in the sense that it derives much in the same way as you might imagine in terms of triangular faces, which you have here. So you have a pentagon pyramid in this particular picture, but in general, this would apply to a variety of them. So each one of these, and we're actually going to derive this one to make sure we understand the why behind it. So each side length is labeled S, and each slant height here is labeled L. So if we look at the way this is drawn, then we can deduce that there are 5 triangles here. And each triangle has an area of 1/2, because it's a triangle, 1/2 base is S, times height, which is L. But we have in general the n number of sides, going around the shape. But remember, n times s, well, that's what perimeter is. It's the number of sides, n times the length of each side, s. So n times s will give us perimeter. So 1/2 perimeter times the slant height. That'll give us the area of each one of these, the total of all of the triangular faces here. So all of those red sections there will be 1/2 PL. Of course, we also have the base to consider. In this case, the base is a pentagon, which of course has its own area that takes a while to find with the apothem and all that. But we'll just call it the base area. So the area of a pyramid is 1/2 perimeter of the base times the slant height plus the area of the base. Again, that's the key formula here. 1/2 perimeter times slant height plus the area of the base. Finally, let's look at the sphere. The Derivation for this formula is kind of interesting. It requires calculus, which we're not quite ready for yet. But let me go ahead and give you the formula. The formula for the surface area of a sphere is 4/3 pi, sorry, getting ahead of myself, is 4 pi r squared, where r represents the radius, as you might imagine. So 4 pi r squared is the surface area of a sphere, the peel of an orange, if you will. Let me show you why that's true. Start this video here. So you can see the sphere being subdivided and then cut into a slice, and then you make a sine wave, which we learned as trigonometry in the context of periodic behavior and lengths going up and down and down and up. And you find the area under the sine wave and you end up getting 4 pi r squared. Not something you have to know for now, but in a couple of years you might, in terms of the y. What you do have to know now is the actual what, which is the formula, 4 pi r squared. So to bring it home, we have the surface area of a sphere, 4 pi r squared, the surface area of a pyramid, 1/2 perimeter times slant height plus the area of the base. We have the surface area of a cone, pi rl plus pi r squared. That's the sector and the circle, respectively. Cylinder surface area, 2 pi r squared plus 2 pi r h, which are the two circles plus the orange rectangle in this picture, respectively. We have sort of a formula for prism surface area, if you wanted to use a formula, or in general, just add up all the rectangles and shapes that you see. All right, so we'll be applying these formulas in Zoom class, and I'll see you then.